In this lesson, we're going to go over a couple of examples of exponential growth and decay. We're going to start with exponential functions of decay when we're talking about things that have a half-life. We talked in class about caffeine having a half-life and all kinds of medications that have half-lives, and how half-life is the amount of time that it takes for half of that substance to be out of your system. So exponential functions with a base of a half look like this. Y equals a times 1/2 to the x. Y is going to be the amount of substance after x half-lives. A is going to be the initial amount, and x is the number of half-lives that have occurred. Be careful with x. It's not time in these examples. It's the number of half-lives that have occurred. And although those two things are related, half-lives and time are not the same. The graph of decay looks similar to this. It's going to have a y-intercept of whatever your initial amount is, and it's going to decay in a curve. We talked in class about how that curve is not going to cross the x-axis, and it's never going to actually reach 0, because remember, it's just cutting in half each time. Okay, example 1 says an isotope of technetium is used to prepare images of internal body organs. This isotope has a half-life of approximately 6 hours. That means it takes 6 hours for half of the technetium to be out of your system once it is injected. Here we have a patient that's injected with 30 milligrams of this isotope. So let's think about what that equation is going to look like. We know it's half-life, so y equals a times 1/2 to the x. Then we know that there's an initial amount of 30 milligrams injected into the patient. So a is 30, so y equals 30 times 1/2 to the x. We're also given that the half-life is about 6 hours, but that doesn't go into our equation. We know x is the number of half-lives, so that's not hours. And y is the amount of technetium in the system after x half-lives. So the 6 hours, while it's going to be useful in different problems, it doesn't go into the equation. This is the equation that represents what's happening with the technetium in the body system. So our first question is, what will the amount of technetium be in a patient after 3 hours? So we have our equation set up. We have that initial amount of 30 in there, and we're given 3 hours. Well, we know x is the number of half-lives that have occurred, so 3 hours, what we need to figure out is how many half-lives is that? Well, half-life is 6 hours, so we're going to do 3 divided by 6 is 1/2. So 3 hours is half of a half-life. So that's how many half-lives that have occurred, is half of a half-life. That sounds funny to say. So we're going to write our equation, y equals 30 times 1/2 to the 1/2, since half of a half-life has occurred. In order to find y, we're going to need to use our calculator. So grab your calculator, and on your calculator we're going to calculate 30 times 1/2, I'm just going to use 0.5, to the 1/2 power, to the 0.5. And we get 21.21. We're going to round that to the tenths place, so about 21.2, and our units was milligrams, so 21.2 milligrams of technetium are still in the body after 3 hours. Well, what if we wanted to know how much technetium was in the body after, say, 12 hours? What if instead of 3, that was a 12? Well, we know a half-life is 6 hours, so 12 divided by 6 is 2. 12 hours is 2 half-lives. So we would plug in a 2 instead. 30 times 1/2, and there's 2 half-lives, so that would be to the 2nd power. And you could just grab your calculator again. 30 times 0.5 squared, 7.5. There would be 7.5 milligrams of technetium in the body after 12 hours. So when you're given time, you just need to figure out how many half-lives that is, and then you can plug that into the formula to figure out how much substance is left. Now this question is a little different. How long in hours will it take for the amount of technetium in the patient to reach 20 milligrams? This problem isn't quite as easy. We can't just substitute in and solve it algebraically. Anytime they're asking for time, we know we're going to need to use a graph. So if we think about this, we start out with 30 milligrams in our system. After one half-life, it's been cut in half, so already it's down to 15. After two half-lives, it's been cut in half again. After three half-lives, that's been cut in half again. So we're down here, and we know we're going to have a curve. It kind of goes like this, that's going to start getting really close to that axis without actually touching it. We want to know when the technetium is down to 20. So that's going to be somewhere, it's going to happen right in there. Well, this line here that I just graphed is the line y equals 20. And the easiest way for us to solve for that point is to do it on our graphing calculator. We want to find that point of intersection. So you're going to grab your calculator again and type in, clear anything that's in there, and type in your equations. The first one is your basic equation for your system. It's 30 times 0.5 to the x. We don't know what x is because we don't know how many half-lives have occurred. We just want it to graph the whole curve. Then we want to know when y equals 20. So we're going to plug in y equals 20. Be sure to check your window to make sure it seems reasonable. X minimum to max, 0 to 10. For most of the problems we're doing right now, that's fine. Remember, minimum number of half-lives, 0. Maximum number of half-lives, 10. If it's not good enough, we can go back and change it. But for most of what we're doing, it's fine. Then Y minimum, the minimum amount of substance in the body system is going to be 0. And then the maximum amount of technetium, she started with 30. So I'm going to set it at 35 just so we can see the top of the graph. I'm just going to go a little higher than the maximum. Then we should be able to hit graph, and we see basically the same picture we had right here, only a little more precise. We want to find that point of intersection, and in order to do that, we hit second and trace, that's calculate. We want to choose the point of intersection, so we choose number 5. And then it's going to ask 3 questions. First curve, second curve, and guess. For this, you can just hit enter all 3 times, and it's going to give us the point of intersection. Y is 20 when X is 0.5849625. Let's round to the thousandths place, 0.585. So Y is 20 when X equals 0.585. Remember that that's the number of half-lives that have occurred. So in order to figure out how much time that is, we're going to multiply that times 6 hours because we know each half-life is 6 hours. So this is going to be, if you think about it, this is just a little more than a half. So we should be getting a little more than 3 hours. Let's check. 0.585 times 6 is 3.51. Perfect. So 3.51 hours is how long it's going to take before the technetium is down to 20 milligrams. So remember, when you're looking for time, what do you want to do? You want to use your graph. The reason we have to do that is because if we take our equation and we try to fill in a 20 for y, we can do a little bit of solving for that, but x is in our exponent. And right now, we don't have the tools to solve for an exponent. We'd need to use logarithms, and we don't know how to do that. So instead of doing this, we're going to graph it instead. We want to find that point of intersection. Okay, our next type is when we have a base of 2. This is when something is doubling. You have the same basic idea as far as your equation goes. Y is the amount after a certain number of doubling periods. A is still the initial amount, and X is now the number of doubling periods instead of the number of half-lives. But it's still, for the problems we're doing, it's still not time. You might notice this graph has changed a little bit. We still have our initial amount is still going to be our y-intercept, but now instead of decreasing from there, it's growing, and it's actually doubling every doubling period. So what does that mean? We're going to talk about some examples, and if you think about a cell, when a cell divides, it creates 2 more cells. When those cells divide, they each create 2 more cells. And then when those cells divide, they also each create 2 more cells. So first we had 1, then we had 2, then 4, then 8. Each time it's doubling. Let's look at this example. We have Streptococcus lactis, a gram-positive bacterium used extensively in the production of buttermilk and cheese, but it also has been famous as the first genetically modified organism to be used alive for the treatment of human disease. Kind of interesting. The doubling period for this bacteria is 26 minutes. All right, so what does your example say? It says if we start with 20 cells of this bacteria, so if we want to write the equation, we know it's a doubling, so we're going to have A times 2 to the x, where A is the initial amount. That's where our 20 is going to go. It's our initial amount. So 20 times 2 to the x. X is the number of doubling periods. It's not time, so we're not going to put this in here yet. And y is the amount we have. So here's our equation. Now we want to do the problem. What is the amount of cells after 2 hours? So a doubling period for this is 26 minutes. One doubling period is 26 minutes. So we need to figure out first how many doubling periods have occurred. Well, 2 hours is 120 minutes. So we're going to do 120 minutes divided by 26 minutes to figure out how many doubling periods have occurred. And it looks like about 4.6 doubling periods have occurred. So we're going to plug that in for x to figure out how much bacteria we have after the 2 hours. So times 2 to the 4.6. This is our initial amount. This is how many doubling periods have occurred. And it's doubling, so that's where that 2 has come from. So we're going to say we started with 20 times 2 to the 4.6. We have about 485 cells at that point. Y equals 485 cells of our bacteria. Bacteria can double very quickly, but different bacteria double at different rates. You can look that up online, but they're all a little different. So if we start with 20 cells of this bacteria, how long in hours, so again we're looking for time, will it take for the amount of cells to reach 5,000? Remember we said when it asks for time, we're going to need to graph it. Now I'm just going to sketch here, but we know that we start with 20 cells of bacteria, so let's put that way down here, and we know it's doubling, so we know it's going to do something like this. We want the number of cells, the amount of bacteria, to reach 5,000. That's going to be way up here. Y equals 5,000. So we want to know where these 2 points intersect so we can figure out how many doubling periods have occurred. Once we know how many doubling periods have occurred, we can figure out how long it's been. But we have to solve for the doubling periods first. So let's graph what we've got. Let's clear out what we had before. We now have 20 cells It's doubling, so it's times 2 to the x. And then we want to know when y equals 5,000. We're definitely going to need to change our window for this. Our y max was only set at 35. Let's get it over 5,000. Let's do 5,500. There's our growth. That's our doubling. And then we see the y equals 5,000 line come across. We want to find that point of intersection. So second, calculate 5 for intersect. Remember, we hit enter 3 times. And that gives us that point right there. It takes, we're going to go ahead and round that to 8. About 8 half-lives before we, 8 doubling periods before we reach 5,000 cells. So let's identify this point. 8 doubling periods gives us about 5,000 cells of bacteria. So it's 8 doubling periods, and we know each doubling period is 26 minutes. If we have 8 of them, then we're going to need to do 26 times 8. So 208 minutes. At 208 minutes, we've gone from 20 cells of bacteria to 5,000 cells of bacteria. And that's how we find the time. Anytime you're looking for time, be sure you graph it first.